medium, and then link layer protocols, and then IP network layer, and then transport layer of the business applications. So this hourglass picture is actually was introduced by the Cunning, yeah, his name is, and everybody, wow, that is really right. What it means is that waist is so thin. Underneath, above it, we have a diverse protocols, but waist in the middle, network layer, it's an IP, single protocol, and then that is the glue that connects everything. So that was the case, but so each layer can do its own thing, and then just provide the services for above layers, relying on the services provided from the layers below and do its own work. As long as the interface does its work, how it is done, it doesn't matter, so that each layer task, the implementation can evolve independently. That's the idea. But somebody actually, they say that, no, not really the case. The older people, yeah, have a love handle. Around the waist we have a more flesh, right? That is really the case that happens, right? So it's not just IP. There are a lot of ICMP, the control protocols around the IP network protocols. This is only about, in fact, data plane, okay? But control plane, these are all data plane protocols. But control plane, the network layer, there are a lot, and other below and above as well. But network layer is where that has the most the control plane protocols. So far, people thought that layering is so great. It really decomposed the tasks, and that led the easy innovation, and that's why we made this internet this popular. It's not because the internet is this popular, not because it's amazing technology, but because it is simple. There has been a lot of other competitors that has better technologies, but over the time they didn't win the race. Simplicity is really important for practical adoption. But so this is what you see that the really emotional, persuasive talk that Scott Schaefer has done. This is an academic failure, very shocking word, right? So in comparison, networking in comparison with other fields in computer science, like OS, database, data structure, and so on, we don't really teach real principles, but just teach backup protocols, acronyms, and networking, folks. It's not easy. That's a lot of people actually recognize that. And then compared to other fields in CS, it has evolved very slowly. This is a really insightful, critical comment. You may or may not agree. I don't totally agree with that, right? But so especially teaching backup protocols, that's not what I do. That's not what we do. A lot of the professors, we do have a good organization, but still, he says that he's a networking person. Still, he would say that. Actually, if you look at the job, the network admin, you get paid more, because not as many. The web development, high schooler can do that, or it says maybe web development, anyone can do that. That's not. Anyone, maybe it's a little over exaggeration. Point is that there are so many people who does that. Network management, not too many. Okay, network management folks who does programming, especially with SDN, programming skill is also very, very important for networking. They might think that it's just a configuration. That's not the case. So the networking is, in other words, not many people do that. The reason is that it's not that easy, right? It's a job security, but it's not. The really, if you want to see the advances over time quickly as other field, this is not really, we are doing something wrong. That's what these SDN inventors do. So I told you there are so many protocols up and below, especially networking question.
Is IoT is a part of network?
What's that?
IoT, Internet of Things.
Internet is the Internet of Things is
part of networking.
Of course, that's a network. So when we say IoT, IoT precursors are like a sensor networks. You have to have a sensing part or the others, some data collection part, and then connect it to the network. Yeah. So the focus is mainly for the link layer connectivity. You might use the Bluetooth, Wi-Fi, but IoT, a lot of things, many applications that you collect data from one, say 2 feet, and then you have a cloud that does the analytics, right? So.
Yes.
So here, if you look at the network used to be pretty simple, Ethernet IP TCP in terms of data plane. However, control plane, we have so many things. IP is a network, the network layer data plane protocol, but it's not a routing protocol. We have a lot of routing protocol, and also there are special control protocols. VLAN, access control list, MPLS, ECMP, firewall, net, the detected inspection, and so on. So this is where the complexity is, and this is where that gives it job security. But in other words, it's a barrier to entry. So control plane, very complicated. Stark contrast to data plane. So how can we make the control plane easier? That's the thing. So the people might say, well, still it worked. See how internet has become, where it is now. It's because the SDN inventor argues that it's not because that it is a simple, not too complicated. It's because just we are too good in understanding complex things, right? But that means that it's a curse for others. And also, this is more philosophical one. The understanding complex things well, that ability is very different from explaining it in a simple manner. Okay, so most of people in technology are good at measuring complexity. Okay. You are still too young, but over the time, computer science is where we have to constantly evolve ourselves. Right. So always there is a new or the emerging field. We have to constantly learn, and we are good at it, right? This is a little arrogant joke, and not So not to. It's with an exaggeration. CS folks can do anything. You can learn, new things well, and yeah. But think about some other field. I don't want to pick. They other field folks. It's difficult for them to get into CS. CS folks, can learn different things easily. But this is you can also do a counter argument. The CS folks have low people skills, low soft skills, and therefore, like businesses, they thing, not much to learn, but it doesn't mean that um, not much to learn. Don't take codes from me, right? That doesn't mean that this post will be successful. No recording.
No, I did. It's the opposite. That's the same I did. I came from electrical background,
Okay.
so I'm doing now CS.
Okay.
So,
Oh,
yeah.
I see. Right. But it's a pretty close build, right?
Yes, it's
Yeah.
close, but it's not explicitly close.
Okay. I see. So, so I mean, this is a little exaggeration, maybe more exaggeration than discussion could be. So, but the extracting simplicity, communicating, explaining in a simple the manner, that's not what we networking folks has been good. That's what we say. But actually, me, I used to, I used to be the person who loves complexity and, like you guys are. But my job is, teaching too, right? So what I have to do is both. And this is really a great joy that doing this together with this. And this, it's just so important in life, not just for the job, but being a parent or just you have to in an industry over the time you have to you're gonna go up in the ladder, corporate ladder, and you have to just communicate with people and extracting simplicity. The good communication is really important skill, right? To making things simple. Okay. So uh, the so far we've been just busy to make things work and focused on complexity. However, now if we want to move on fast, we have to really focus on extracting simplicity. And this is where we didn't do good. And it's really important thing is that abstraction. In fact, abstraction is a part of computational thinking. Computer science, the way we think, computational thinking, that includes abstraction, divide and conquer, pattern recognition, parallel programming, parallel processing. These are kind of embedded in our thinking, right? That's what you do. And abstraction, I gave an example like, children's anime. What could be that? Really, these days, animation are too sophisticated, more realistic than real thing. I'm not talking about that. Like a Dora, or whatever. Really, children, they want simple things, right? So facial, it's just a circle. Face is a circle, and the skin tone, texture, it's just all flat, right? That's an abstraction, simplicity. Just having a circle, dot, dot, you know that's a face, right? So that's example of the abstraction. And rather than focusing on complexity, we have to do some abstraction. And that is what the programming area in computer science has been really good at. These days, AI or whatever, just use a Spark, all those things. You just use an API, very simple API, right? You don't really worry about what's happening underneath. Well, cloud computing students, what's happening and you appreciate it, but a lot of other people may not, they recognize it. We have classes, we have, the really higher level abstractions. The older times, it used to be machine language and then assembly language, low-level programming language. Maybe back the C is a little, may say, still C allows you to think about the pointers and so on, right? So it's important, good one. But for some people, it may have a difficulty in writing codes with memory management, right? So if it's a programming languages, anyway, we have a higher level abstraction that relies on whatever, the abstraction that comes. So like even memory, you don't worry about this variable, where is it located in physically, right? The storage, you just use a logical unit, not really worrying about the physical location. So that's where we do the abstraction, and networking we need that more. Then what can we do about the control plane abstraction? We need to have a powerful control plane abstraction. So that's where they start the story. Let's define the problem and then decompose what kind of abstractions we need. The first thing, what do you think? If you were to, newly design, think about the new abstraction of a network control plane, what's the first thing you would have? I want you to have just a few seconds of thinking at that point, and then they see how whether you can appreciate this. So, first thing that we need in terms of abstraction is a global network view. Previously, routers, I'm new in this network, and then I run a protocol and see what are the other routers and links available, what's the cost, and then from there, it does Dijkstra, or it does compute the routing algorithm, and then produce a forwarding table. Routers doesn't have eyes, noses, hands. It doesn't know about the presence of other routers. It will just exchange information and then have an inference of the network. Rather than that, let's just assume that router, the global network view is available. That's how the abstraction starts. So global network view meaning graph with a nodes and links. Okay? So let's have a global network view, and it can be made available as an API. For that to happen, there should be a network operating system. Okay? And then the things important that can be given as an API. So this is the link state routing that uses Dijkstra algorithm. This based on global view. This Bellman port distance vector algorithm, in fact, it never knows the global network view. It just computes what's the path cost based on its neighbors. So this is a completely distributed algorithm. We are going to trash it, and we can use this Dijkstra algorithm over a graph that has a global view of node and links, and then the routing can be given as an API. Now routing becomes just application program on top of this control plane. So routers used to run a distributed algorithm with the neighbors. Now we'll have an abstraction called network operating system, and it will just spit out the global network view. Then the routing will be a control program, control app on top of this graph. Do you have a goosebump? Really, it's a really radical idea. Routing, access control, firewall, it will be all just app. Who hated this the most? Think about it. Router vendors, Cisco, Junipers, what they do, their hardware advancement is not that fast, but each time they have a new feature, small feature added, they package it. Oh, this is amazing new one, and they sell to AT&T, T-Mobile, Sprint, and that becomes their new revenue. Now it's all becomes just an app in the software, right? They used to embed this new feature with the hardware, and they sell hardware with it. And now it becomes just a software. They don't get to sell new hardware. However, it became a big movement, and the way things happen is that if you don't ride on that movement, you're gonna be outdated. So Cisco jumped in, and they try to do all things to their liking, and then still SDN Cisco product it's making. So they are still leading player here. But anyway, still these things are now done in software. It's an amazing thing for researchers. We can do new things.
So if the routers, like every time there is a new features, we need the Cisco try to add it, right? But now it's all software, you're saying. But if you want something like more something advanced, then we don't need hardware then.
Oh no, we do need hardware. We do need a powerful hardware, right?
Yes, the old hardware will not support. Suppose we
New features. Yeah,
new
that's
features.
absolutely. Yeah, yeah. Hardware. I'm not. So I'm not saying the hardware is not important, but the 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 business approach they used to do is not
Okay,
valued
got
as
it.
as hardware is really important. So don't be biased. They don't take it literally, right? So, but when I say that I'm a software person and it's amazing, but I also, really encourage you. It's I also say a lot of times it's important for us to know how hardware works to make an improvement. And look at all the cloud computing companies. They used to be software companies. They make all the hardware. Google, they did just a search engine software. They make all kinds of hardware. They make phone, right? Without actually hardware infrastructure, they also sell cellular network too. I use Project Pi, so the Google, right? Um, Apple, Amazon, the Apple is a different. The Microsoft is the largest software company, but they all make hardware as well, right? Hardware companies they are having hard time to have a software thing. AT&T, T-Mobile, T-Mobile can be different, but earlier ones, Sprint, they had all the infrastructure hardware, but they failed to create a big revenue out of that. Right? Yeah. They might in the future, which I doubt. So, and then next, the abstraction is that the network model, right? We need the network specification to be abstracted. So previously, the global view, what's the abstraction we had? Distributed state. It becomes abstracted as a global network global view. So state was abstracted. Now specification, um, needs to be abstracted, and the mapping between this the logical network to physical. So the configuration specification, we want to have an abstracted manner, but in the end, hardware has to be there, so there should be some mapping from configuration to the logical configuration to physical configuration, and that has to be done underneath. So for that, we need network virtualization. We have seen before, here's a physical layer, physical network, and then logical network. There's a mapping from logical to physical, right? So now first we have a global network view. On top of that, we want to have a special, uh, specification necessary for this research or that practice and so on. This mapping has to be done. It will be separate from what needs to be done. So previously so far we had a global network view offered by network operating system, and then control program. The other things were the control programs. Routing becomes control program. Now we want to have another layer of abstraction, that's a network virtualization. So out of this physical view, we can have various arbitrary network virtual networks, and then this translation from peer to peer has to be done. Right? So we can, all these things, access control, traffic isolation, routing, TE stands for traffic engineering. It's a civil engineering term for, traffic light. You engineer, control traffic with the green light, one car passes, things like that. That's a traffic engineering. And we can also do control of the traffic in network as well. And this is also all these work, control plane work, it can be done with this virtual, in a virtual level, and then there should be a compilation. So it's almost like, all the politics, the president or the upper, upper layer politicians said, let's do this. And then all the implementation done by the, government, right? And that's what's if president has to think about all the details, he won't be able to plan in a larger scale, get a lot of things done. This separation of abstraction actually makes things simple and scalable. So that's what it has. So this with this SDN, it's great for research, great for cloud computing too, where we can have a multi-tenant users. Each tenant, each corporate company with a lots of branches, they can have their own private network, right? These things, actually, if you think about it, it's easy with SDN because we start with, this is what virtual network we want to do. It's pretty impossible, very difficult without SDN. So I told you, Martin Casares, this paper was published in 2008 or so, and then 2009, they it's becoming more visible. That is the time cloud computing was also becoming more, known. Remember the Salesforce video that I've shown you? That was 2009. AWS, they around 2009, right? So many things are happening at the same time. The SDN, when they motivated, they didn't say it's great for cloud computing, but ended up being so important for cloud computing. Martin Casado's Nisira company was a separate, the individual company, eventually bought by VMware, right? The virtualization technique company. So what about the forwarding? How the packet is being forwarded, and then for a switch, you can also think about a little more decomposition there. But we are not going to go detail. But the important thing for you to know is that protocol called OpenFlow. So the control direction is coming from the remote controller. It has to be acted upon by the switches. And sometimes switch has to report to the controller. That interaction has to be done. And that is, you don't want to, so that's a logical thing to do. But if everybody does on their own way, then its interoperability will be poor. In networking, standardization. Networking, by definition, there should be at least two talking to each other. You cannot just by yourself, right? So the more nodes or the more entities to get connected, they have to speak the same protocol, and the SDN community, Open Network Foundation, they they went through a lot of revisions and then standardized the protocol called OpenFlow. So what it does is that it has this entrance. Let me give you the example first. Yeah, but before OpenFlow, just one more thing. There's another thing called P4. P4 stands for Programming Protocol Independent Packet Processing. I didn't actually memorize all this. You see me turning, right? So P4. So SDN is really about the separation of a data plane, control plane, and making control plane work. You know, logically centralized. It's all about network layer and up. What about the link layer? Let's do also the to the software approach, and that is P4. So here, the keyword you can, well, it's all important. All P is important, but the first word, programming. In other words, software based. So really, the software folks has a more avenue. You can work in any companies, right? No companies that doesn't need no companies. There's no company who do not need the software people, right? So even switch, we can do a little more sub-programming to make things more flexible. So open networking P4. This is through, of course, Stanford, Berkeley, and also Princeton folks. And then and many other companies in academia work together in this. So this is about data plane abstraction. So far, SDN, we talked about the control plane abstraction, and there has been a movement on data plane abstraction. Now going back to SDN and OpenFlow. So remember, controller is remote, logically centralized, that computes the forwarding table for each of the routers in the network. This forwarding table, we also call it now flow table. Okay, so flow table means that, okay, so I'm just trying to control time so that because it's the last class and we need to have all things. Yeah. So here, rather than routing table, now it's called flow table. Flow definition, it can be generic. It can be generalized. Previously, routing table, what is it? Destination address prefix. Is it going to 134.128 something? Is it really UNKC network or not? Right? UNKC network, this interface. That's what the forwarding table entry used to have. Nowadays, now with flow, the destination network prefix can be just an example of flow. But flow can be defined in various ways, so it's more generalized. It has, so previously header and interface, right? Now with the SDN, it has a header, some measurement counter info, and then action. Action, not just a forwarding interface, but there can be different actions too. So it's really generalized forwarding. In other words, the flow can be really various depending on the pattern of the packet header. So there's a packet header field pattern that matches, and the action previously was just use this interface. That's it. That can be considered as a forward. Previously, packet dropping, if there is no matching entry, it's dropped. Now it says explicit drop, forward, modify. Sometimes you send the packet to the controller. Generalized actions are possible. You can also give a priority of the traffic. Like this is a special, this is express expedited traffic. You forward it as soon as possible. Don't put it at the end of the queue. Okay? So that's possible, and also it does constant monitoring, packet count and byte count. So this the controller and switch. The interaction protocol is called OpenFlow. OpenFlow gets the information from the switch. So controller to switch, it gives the flow in the table information. And sometimes controller can ask some information, how many counts you have so far, things like that. So it's management information request is possible, but also gives the flow table entry. And also, switch can send something to controller too. Like this is a new packet. I don't know what to do. So that can be done. Asynchronous message meaning not like new packet coming in, immediate processing. Separately it will send. The switch will send a message to the controller asking what to do, or here's an error, and things like that. So again, controller is remote. Here's a switch. This switch is capable of open flow, so we call it open flow switch. Communication protocol is open flow. So open flow should run both at the controller and switch. This is a controller side, and this is a switch side. Eventually it gets the flow creation. So really I hope this example gives a bit one. So you can do something like this. It supports wildcard. So not just the previous traditional IP routing, it's really destination address based only. But now we can do this. Source address, destination address, in fact, TCP, transport layer, network layer, link layer headers, all of them can be used in the flow definition. In this example, source network and destination network, you can specify at one of the entries and say, if it's coming from that network and to this network, drop the packet. If from anywhere, destination network is this, then forward it with interface 2. Okay? You can say from one source, whatever destination, send it to a controller. For maybe control debugging purposes, you can do that. See, here the table entry, you can have TCP header, IP header, link layer header, VLAN header, physical port info. You can have any of those things, put it in a rule, not just IP destination. See, it's a generalized header. And then action can be forwarding, sending to controller, dropping, some processing, modifying fields, packet marking is all possible. And then also statistics, monitoring, counting. Right? So that is really amazing thing. And here's an example. So in the exam, I might ask you like this. Show this. What is this about? And out of the choices, it's a destination-based forwarding. So look at this table. Wildcard, 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 anything. But if destination is this, then forward it with this interface. So it's really destination address-based forwarding, right?
Can you explain one more time?
So here's the right. Yeah, please feel free to answer. So if you didn't see this, what kind of forwarding is it? What I'm showing is that this open flow can do the generalized forwarding. It does what it used to do, what router used to do, but it does more than that. In fact, it can do firewall too, right? There are so many firewall companies. We also still buy firewall boxes, that does the packet processing. Logically, with SDN, you can configure it really easily. So here, what it shows is that regardless of any other field in the packet header, you just look at the destination IP address, and if it matches with this, forward it with interface 6.
Okay.
That's what it means. So what kind of routing is it? Destination address-based routing. Okay. Now suppose if you didn't see this, regardless of any header, look at the TCP port, destination port 22. What is this?
Default.
TCP port 22. What is it? It's a SSH.
SSH, yes.
SSH traffic drop. So in our from home, unless SSH is enabled by default, you cannot access university network through SSH. This is what I firewall does. Why the destination port? Destination port is about the application. You can block Skype traffic. You can block, some, social networking traffic. All those different applications have their own destination port number. What is the port number for web? HTTP port number?
HTTP, yes.
What's the port number? 80.
80,
right?
yeah.
What's the email? 25? Yeah. So how do they know this is the email? How do they know this is a web and sending to a web server? Based on transport layer port number, right? So in other words, application specific handling, it means that the port number, right? So this is what it does. Here, it says any traffic coming from this source, you drop it. You can block some node. I have like a project website, and it shows us periodically what are the IP addresses that are blocked. Some strange traffic try to bombard my the web server. You get that info. What do they do is they block the traffic. This is how to block some source. And this is a destination MAC address based forwarding, right? So I can also ask you, what should be this field to do, say, you want to block SSH traffic, or you want to forward traffic from this source to this destination using this interface. You should be able to control it, right? Of course, you should be able to do it in an open flow configuration, but this is a logical explanation. So really, the match and action can be done in different ways. So this is open flow. This open flow can do a lot of things, generalized things. In terms of like router, it can do routers thing, switches thing, firewalls thing, nets. So what router used to do, what switch used to do, what firewall boxes used to do, what net box used to do, you can all do things with SDN, open flow. So think about router. What it does is that long distance destination IP prefix based connection. So we just have the IP header destination prefix, and then do the forwarding to a right interface. What about switch? Switch is a layer 2 box device, so it's really based on destination MAC address. Switch does not do routing. It doesn't know what is the shortest path. It doesn't have that intelligence, but it knows that which node is connected to which interface. How does it know? Just by observation. In the beginning, it's a plug and play. In the beginning, it doesn't know anything. In the beginning, it will do flooding. Hey, this is a traffic for this destination address. And somebody will reply it, looking at that, oh, that destination is connected to this interface. Put it in the table, and then in the future, the traffic comes to this destination. It doesn't do the flooding. It only talks to this. So that's how switch works. And that is just basically put the destination MAC address and then forwarding or drop. What did I say? Forwarding or flooding. Okay. Flooding means you send it to everyone. Broadcasting it. Like every switch here. What about firewall? You have seen that before, right? Typically what it does is that it uses a TCP port, UDP port numbers, but sometimes you might want to use IP addresses as well. So have some field for IP addresses and port number, then you can do permit or deny. Firewall typically, you can selectively permit or deny some traffic. Right? Network address translation. What it does is that internally you use a 10.x address, private IP address. That name is like number 1, number 2 in your family. Your parents might call you, hey, number 1, number 2. Like, what about your friend? She or he is also number 1 or number 2 in the family. So number 1, number 2 is a private, internally unique. At your home, you are the only number 1, but not the other family, right? So 10.x address, that's a private IP address. To get connected to the other people in the rest of the world, you have to have a globally unique name. Your family name, first name, supposed to be globally unique. Oftentimes it's not. In IP, the routing, it has to be globally unique. So that address translation has to be done. It's done through the port number and IP address combination. And that action also can be done through OpenFlow. So amazing, this really generalized the action, generalized the packet header pattern. Match the pattern and the generalized action. This combination really makes things versatile, right? A lot of things you can do. So here's an example where you suppose in a test bed you have set up like this, okay? So from this node to this node, there are 2 paths, either this or this. But for your experiment, suppose you want the traffic to go through this. Then you can do this. Any traffic coming from both of these hosts forwarded to interface 3, not interface 4. And here, this traffic forwarded to 4, not somewhere else. And then you can go to different hosts, right? So really, SDN, you feel like you can do anything, right, in terms of routing, right? So that's what it's unique. Questions? The last one, I would say just let me focus on your exam question, okay? So Google's data center. What about the AWS data center architecture? What about the Azure? They didn't publish, right? Google published. So they also have done the data center network architecture paper. Previously you saw GFS, right? MapReduce paper. Spark from Berkeley, but it became Google's board, right? So all these Google paper, that's what we are based on. The paper called B4. Have you heard of B4 before?
Yes.
When? You have?
Yes. When I was working with
in this class, yeah.
Yes, in this class.
Yeah.
Yes, when we're doing the assignments, I see some of the things in the Google. They were offering some of the things. I thought I see it. That's
no. But you have heard in the video, Google's data center tour, the first week's video. They talked about B4.
B4, yes.
Okay, why B4? I don't know exactly. It might be some internal name or.
Oh, I can't. I misunderstood. I thought it's.
Oh, we also talked about P4 today. Programmable packet independent.
Yes.
Packet forwarding the paradigm, right? P4 is a data plane. So I'm talking. Just let me just point the exam question. That means it's really long-term takeaway for you to have, right? The even job interview. What did you learn about from the class, beginning class? Some of the keywords I'm talking about. So P4 is the SDN OpenFlow is all about the control plane abstraction. P4 is a data plane abstraction. I've shown you just one slide. You just know what it is. B4 is the Google's network architecture. Google's network architecture, data center architecture, private SDN. So what the amazing thing they have shown is that SDN, of course, it started from industry. It's all great promise, but a lot of other academic papers have the great promises too. Okay, does it really matter? Is that it's going to be implemented? Here, tada! Google published a paper saying that we have implemented SDN, not just there, in WAN environment, not LAN environment. Within Google, they have a WAN. They have a LAN and WAN. Data center LAN, they have a multi-data centers wide area network connectivity. They use SDN for their WAN network. That's amazing thing. Production network, really large scale network, not just LAN, but WAN. And one more thing, we had really high, we achieved high utilization. I think it was, let me go, did I say, over 90 something, near 100%. That's almost unheard of. Typically what the admin do is that above 60, oh, we need to do over provisioning. Otherwise the system may crash, people will complain, and over provisioning is already starting from 50-60% utilization. They say we did an SDN in production network over WAN, and we achieved the utilization over 90%. That is really big eye opener for everyone. These days, the SDN is a critical component of data center networking. So that is the paper. Jupyter is, Google does hardware as well. And this spelling, what is it? J-U?
Jupyter.
The spell, can you spell it?
J-U-P-I-T-E-R.
P-I, not P-Y. Right? This is their name for hardware. So it's really, they are not just, they started from Dell computer with a Cisco routers, switches. They are actually making servers. They build their TPU, all they integrate, of course, not from the very scratch, and they use the NVIDIA and all other companies, but they really go hardware too, and it has they have gone through multiple revisions, and Jupyter is the latest one that is published. So what you see over here is that, look at the cabling. By having their own one, they try to minimize the cabling, power consumption, and energy dissipation, as everything as efficient as possible. And then this is a Jupyter topology, highly redundant. The redundant, not too many, but the 2-3 later, the hierarchy. So really they focus on the scaling out. You have heard this one a lot. Scale out rather than scale up. So every aspect they could pay attention to that. So this is a Jupyter Rex, uses OpenFlow. Yeah, scale up. So this is the part that we didn't get to talk about, data center TCP. I'm going to have a recording available next week. Yeah, next week. So in addition to today's a really fun hands-on session for COVID data visualization, the work, I'm going to also make the DC-TCP available. This is another thing you have seen in the Google's data center tour. They talked about this DC-TCP. Please watch the video again. Right? Then you will understand now a lot more. They talked about the Borg, Kubernetes, V4, SDN, yeah, all these things. Okay, so let me stop here for today. Good luck with your exam. Today's class is really important. I'm glad that you guys joined. Some of things I went through quickly. Some of things I really emphasized. At least those keywords you need to know what it is. I'm gonna make the quizzes available. There was one time student telling me, "Oh, I learned a lot while taking the exam." So taking the solving the quiz, it really helps you, right? So I will make the quizzes available without the access code. So study that before the exam. Question?
Yes, in the beginning of this, after the mid 2, you have talked about CDN.
Yeah, CDN is going to be part of.
Yes, it's going to be part of, but the topic
from the
you
beginning, entire CDN.
intercedent is not there still.
That's going to be added. So I'm going to.
The slide is not there.
explicitly
Yes. No. I've
That's impossible.
uh,
Nobody told me. Can you double check?
yes. So when I was going through the video,
How should I know? I know. I'll do it today. Okay. And really, yeah.
yes, after this slide there is no more slide.
Yeah, I think that's it.
That's the end, but in the video I recorded the video, so that's I was saying after this slide you're talking about more slides, so I was
Did I do video?
no, I made the video, I saw it, then I thought there will be more slides. Where is the more slides? I couldn't find it.
I might have. So what's the slide earlier than that?